Welcome to NGA's AIA accredited presentation, Thermal Bridging Considerations at Interface Conditions. NGA is a registered provider with the American Institute of Architects Continuing Education Systems. This course on thermal bridging considerations is registered and accredited by the American Institute of Architects, and one learning unit is awarded to architects for completing this presentation. This presentation discusses thermal bridging as it pertains to the thermal performance of fenestration systems and their interface with the surrounding conditions. The learning objectives for this course are to define thermal bridging and associated terminology, discuss thermal bridging as it pertains to the interface between glazing systems and adjacent construction, explain potential strategies to address thermal bridging, and compare and contrast the roles of designers and fenestration suppliers in accounting for thermal bridging. Glass fabricators, framing suppliers, spacer manufacturers, and sealant manufacturers combine their products to create an overall energy rating for a glazing system. Current modeling and testing standards determine the U factor of frames and glass as a system. These systems are installed within the building envelope as windows, punched openings, window wall, or typical storefront elevations. Other systems, such as curtain walls, are installed to the exterior of the structure and become the building envelope. Beyond the U factor of the window or curtain wall itself, how the fenestration system is installed and interfaces with the surrounding wall or roof assemblies can influence the overall thermal performance of the building envelope. Thermal bridging occurs when building exterior cladding or structural components with high thermal conductivity penetrate or bypass insulation, creating a path of least resistance for heat transfer. ASHRAE Research Report RP 1365 says, the reduced thermal resistance due to thermal bridging through steel and concrete framing can have a significant impact on the whole building energy performance. Uncertainty about the thermal performance of the building envelope can lead to inefficient design of HVAC systems, building operation inefficiencies, inadequate condensation resistance at intersections of components, and compromised occupant comfort. Similarly, BC Hydro's Building Envelope Thermal Bridging Guide says, building envelope thermal performance is critical consideration for reducing space heating loads and will be an increasingly important factor as authorities strive for lower energy consumption in buildings. It has become more and more evident that the thermal performance of the building envelope can be greatly affected by thermal bridging. So what is thermal bridging? We mentioned on the previous slide, it creates the path of least resistance for heat transfer. In more detail, thermal bridges are localized areas of high heat flow through walls, roofs, and other insulated building envelope components. Thermal bridging is caused by highly conductive elements that penetrate the thermal insulation and/or misaligned planes of thermal insulation. These paths allow heat flow to bypass the insulating layer and reduce the effectiveness of the insulation. An example of thermal bridging is a break in the continuity of the thermal resistance line in the building envelope. Specifically in this example, a steel beam or balcony penetrating the wall insulation will create a path for heat transfer. This pathway could lead to heat loss and decreased energy efficiency, as well as potential cold points that can lead to condensation within the building envelope on exposed interior surfaces. Model energy codes typically address the performance of individual components in the building envelope. This includes the U factor and solar heat gain coefficient of fenestration products, as well as the R value of opaque wall construction and roofing assemblies. Model energy codes typically have not addressed the intersections of these components or penetration of the insulation. However, as they increase in overall stringency, some codes are beginning to address thermal bridging. Why is this important? Building envelope thermal performance is a critical consideration for reducing space heating loads and will be an increasingly important factor as codes strive for lower energy consumption in buildings. Thermal bridges allow uncontrolled heat flow to bypass the envelope insulating layer, introducing uncertainty of thermal performance, and thermal bridging enhances the risk of inefficient design in HVAC, building operations, inadequate condensation resistance at interfaces, and compromised occupant comfort. For example, the Seattle Energy Code increases the amount of continuous insulation required in opaque wall construction based on percent area of metal penetrations compared to a wall with minimal metal penetrations, or thermal bridging. Energy codes in Vancouver and New York City require that thermal bridging details be identified on drawings and be accounted for in all performance modeling. Most notably, ASHRAE 90.1 has been working on comprehensive new requirements to mitigate thermal bridges in many areas, including roof edges, parapets, intermediate wall edges, balconies, masonry shelf angles, and the wall to fenestration intersection. These requirements apply to colder regions, ASHRAE's climate zones 4 through 8, and are included in the 2022 edition of ASHRAE 90.1, which is referenced in the 2024 International Energy Conservation Code. It can be helpful to understand the terminology associated with thermal bridging. Thermal bridges can be characterized as either linear or point. Thermal bridges associated with the interface of fenestration and surrounding conditions are generally linear thermal bridges, as shown in the photo on the left, where balconies bypass the insulation. Point thermal bridges are shown in the example on the right. These are often associated with supporting exterior components and glazing systems, such as signage, canopies, sunshades, louvers, etc. In this example, steel balconies with a big beam are penetrating the insulation on the left and right edges of the deck, as well as at the location of the small plate connecting to the tie rod that is helping to suspend the deck. Examples of linear thermal bridges include balconies, shelf angles, or fenestration framing where the installation bypasses the wall insulation. Thermal bridging on the building at balconies, bypassing insulation, acts just like radiator fins on a motorcycle engine. Linear thermal bridges are characterized by psi factor, which is the thermal transmittance per unit length, in units of BTU per hour per foot per degree Fahrenheit, or watts per meter Kelvin. Examples of point thermal bridges include localized penetrations of beams, columns, or anchors where the installation bypasses the wall insulation. Point thermal bridges are characterized by chi factor, which is the thermal transmittance per penetration area in units of BTU per hour per foot per degree Fahrenheit, or watts per meter Kelvin. In this example, using the big beam penetrating the insulation on the left and right edges of the deck allowed them to space the balcony a little out from the wall to allow the wall insulation to continue behind the center part of the deck, versus just mounting a steel beam across the whole width of the deck where it meets the wall, turning a potentially very large thermal bridge into a much smaller one. The energy codes account for thermal bridges in two ways: simple prescriptive strategies and more complex modeling. The simple approach can be deduced to a basic concept of thermal line or thermal plane. The more complex modeling approach uses modeling of assembly details to generate the psi and chi factors that were described earlier. For the simple approach, when looking at details at the window and wall interface, many designers are used to the idea of drawing and looking for a continuous water control line and air leakage control line. The same concept can be applied to thermal bridging by looking for a continuous thermal line. The architectural drawings typically represent the vision of the design team for the exterior cladding. Most notably, the elevations and sections indicate where the glazing system framing members are to be located, the size and type of glazing infills, etc. While everyone, from architect to glazing subcontractor, recognizes the information conveyed in typical vertical and horizontal section cuts through the glazing systems, it's critical the perimeter details indicate the proximity and relationship of the glazing system to the air and water barrier locations in or on the adjacent construction, and how any anchorage details, sealant joints, and other components may interact or impact the glazing system. The glazing subcontractor and framing manufacturer should be able to determine how water can be drained from the glazing system to the building exterior. Establishment of the air barrier transition from fenestration system to perimeter conditions is equally important. Now we'll reference the thermal line illustrated in red. Just as designers and engineers look for a continuous line connecting the constructions to form the primary air and water barriers, they should also now look to construct a continuous thermal line connecting the insulating materials across the transition details from fenestration to surrounding construction to create a thermal barrier between components. This example shows minor conductive bypasses, not ideal but not poor. The example on the left shows a thermally efficient design with the glazing, frame thermal break, and wall insulation all aligned as shown by the red thermal line. The example on the right shows a poor design from a thermal bridging aspect. Even though it is an efficient window with high-performance glazing and thermal break, the misalignment with the wall insulation, noting the non-continuous red thermal line, leaves a diagonal path for heat loss to completely bypass all the energy-efficient components. For fenestration assemblies, whether a punched opening window or a curtain wall, the concept of a thermal line leads to this ideal scenario of alignment of the insulating glass units, thermal breaks within the frame, and insulation and surrounding construction without any significant bypasses. This ideal is not always possible when considering the many functional design requirements regarding structural support, water management, etc. However, better alignment will generally result in less thermal heat loss and an improved or lowered psi factor. Note in the diagram, a flashing is shown which is exposed to the elements and passes beneath the curtain wall and into the warm side of the building. While this flashing isn't visible, surely condensation will occur and as such may cause issue. The simplified prescriptive requirements proposed for ASHRAE 90.1 also try to encourage this practice of alignment and/or a continuous thermal line as much as possible. ASHRAE 90.1's primary requirement is to align the glazing layer within 2 inches of the wall continuous insulation or within 2 inches of the exterior side of the cavity insulation where there is no continuous insulation. Ideally, thermal breaks within the frame are also aligned with the glazing, and the benefit from doing so will be reflected in the lower U factor rating for the product. This photo shows a residential building with the sills and jambs extended to allow the window to sit over the foam insulation when installed. This example shows how to properly account for thermal bridging. When they add in insulation, it will line up with the window. Aligning the glazing system and the wall insulation is not always possible because of functional considerations such as structural design or simply for design aesthetics. Therefore, ASHRAE 90.1 also includes other options for recessed windows or offset construction. In that case, the goal is to continue the thermal line from the continuous insulation to the window framing, covering any exposed area with insulating material with R value greater than 3 or thermal conductivity less than 3 BTU per hour per foot per degree Fahrenheit. This would also include the option to mount the fenestration within a wood buck. It is not required that the insulation be under the frame, as careful consideration must be given to the attachment and support of the window, as well as proper water drainage. In all cases, the intent is to maintain a continuous thermal line as much as possible and to minimize interruption of the thermal line, thus creating thermally bridged details. The more complex approach to thermal bridging involves comprehensive heat transfer modeling of assembly details at each interface. This modeling generates psi and chi factor thermal transmittance numbers for each construction detail. These numbers can be used to adjust the effective U factor of the envelope assembly and to account for the greater heat loss in whole building performance calculations. Psi and chi factors can either be modeled for each custom assembly detail or pre-calculated and provided for common constructions. These values would be necessary if using the performance path of building energy codes for compliance. Refer to the BC Hydro report for psi and chi factors of common constructions. In some cases, the manufacturer may have this data available as well. Thermal modeling and testing presently do not typically include the perimeter joint or any thermal insulating materials that may be placed in them, although it is possible that they could be added to get a more accurate prognostication as to the thermal performance occurring or not at the perimeter of the fenestration. Based on how the general contractor divides the scope of work and which contractor is going to do what, at the sequencing of the work around these perimeter conditions, the relevant subcontractor's submitted shop drawings should provide the details needed to conduct an energy model of the system. Based on this fragmented division of work, it may be impractical for a single subcontractor to compile all thermal modeling and testing under one scope of work when its scope of work terminates somewhere at the edge or in the middle of transition detailing. The design team is normally in a better position to compile model and test data from the glazing systems, the surrounding construction, as well as that for materials used for the interface. Data may also be used to determine if the interface should be thermally enhanced to meet whole building energy objectives. The design team may use the data to determine if the enhancements are cost-effective compared to the anticipated energy savings. Modeling can also provide useful information about surface temperatures to help locate cold points below the dew point at different design conditions, and therefore help identify potential condensation areas. This diagram from ASHRAE illustrates an example of thermal bridging in floor slabs. Note the exterior is on the right side of the diagram. Fenestration suppliers may provide standard industry modeling, Lawrence Berkeley National Labs Therm program, for example, and or test reports the design team can use to prepare overall energy models. Shown on this slide is a partial list of data that may be used to develop the energy model. Availability may vary by manufacturer or supplier. In addition to the thermally bridged details, there are many other issues that must also be considered at the same time. Edges or perimeters are often the location of many functional aspects of a glazing system interface with adjacent construction. While a drawing of a detail is static, the actual construction of that joint is not. It is often a dynamic joint and should be detailed and executed with that in mind. A few of the more important considerations to be aware of when detailing these joints is as follows. First, accommodate movement of glazing member deflections from wind load and thermal expansion or contraction caused by seismic events, live load deflection, column foreshortening, etc., which often occur at the perimeter joints. The joint at the head of the glazing system typically experiences the most movement from live load deflection and thermal expansion or contraction of the glazing system, but jamb and sill joints will be impacted as well. Any continuity of the thermal line in the glazing system to the surrounding thermal insulation should be able to handle the potential amount of movement at the location in question. There should be no degradation of the thermal line continuity or its insulating properties long term. For example, on a typical curtain wall, a plus or minus 3/4 inch perimeter joint around the frame is normally utilized. This allows for building movement which may include actual structure movement, glazing system deflections, thermal expansion and contraction, variation in surround opening tolerances, and sealant movement capacity. A second consideration is water weeping. This occurs when water is occasionally wept from the glazing system into the sill or jamb perimeter conditions or is collected in head conditions of the glazing system. Any water collected by the glazing system is first directed to the exterior side of perimeter joints, outside the air and water line, then redirected to the exterior of the facade. Thermal continuity, detailing, and construction must not interfere with any water migration strategies the glazing system uses to redirect any water to the exterior. An expectation that thermal continuity will be 100% through these details at the joint or in the adjacent construction is unrealistic with most present-day glazing systems. A third consideration is insulation. Adding insulating materials at perimeter details should be done carefully to avoid shifting condensation or localized cold spots within the glazing system or surrounding conditions to a point where the condensation cannot be collected and redirected to the exterior. Insulation should also consider any movement that might occur at the joint and avoid interfering with anchorage detailing, such as shims or connection to the structure. Covering interior exposed surfaces to add thermal continuity can adversely affect surface temperatures. The material in contact with the sealant must be compatible with that sealant, normally based upon compatibility testing. This is also true of any means, methods, or materials used to affect thermal continuity. Pre-construction and on-site testing by the sealant manufacturer and/or the installer should be completed to verify adhesion and compatibility of the sealant to adjacent materials. The designer must be aware of the importance of maintaining a high level of thermal continuity in the detailing of perimeter conditions and how they may possibly interfere with other functions of the glazing system. For example, a design incorporates windows where the plane of glass varies significantly with the exterior face of the surrounding construction. For instance, it could be shallow at 1 inch to 6 inch offset or deep with 6 inch to 12 inch offset or more. The masonry or precast panel returns that transition from exterior face to the glazing to create the opportunity for the glass to be significantly located at some distance from the insulation to the adjacent construction. Detailing the size and location of insulation should be included in both the construction documents as well as the specifications. The specifications describe products and performance values for the materials to be furnished. Cost-effectiveness of adding thermal continuity between glazing systems and surrounding construction is not easily recognizable from the glazing subcontractor's perspective. Involvement of the HVAC and mechanical engineering profession is recommended to compare the cost of the material and labor of thermal continuity details with the expected energy savings that could be realized. This analysis should be completed typically by the design team prior to the bid documents being issued, and could then be used to determine whether the details should be adopted. The glazing subcontractors typically do not have access to the information required to complete this comparison. For a curtain wall, if you bypass the insulation, you have cold air on the backside and aluminum or steel coming straight down. You have energy loss but also condensation if done incorrectly, that is, if a bypass is not thermally broken. Referencing the images on this slide, was this building designed with thermal bridging in mind? The answer is yes. The building was designed to minimize thermal bridging. If you look closely, they did separate it. There is an extension. They were careful to separate it from the rest of the building. They reduced what would have been a long linear thermal bridge into smaller point thermal bridges. In summary, the installation of a fenestration system and how it interfaces with the surrounding wall or roof assembly require more insight than simply U-factor. They can affect the overall thermal performance of the building envelope, but also impact other fenestration and construction performance criteria, notably air and water resistance at transitions. This is an evolving topic with future developments driven by codes and industry standards and best practices. Partnerships with fellow design team members will make a positive impact in accounting for proper component compatibility and construction. This presentation is also available as a design guide from the National Glass Association. Use the QR code on screen to be taken to a site to download the design guide now. There are a variety of additional industry references on screen that may also be useful. Thank you for participating in this presentation on thermal bridging considerations at interface conditions presented by the National Glass Association. Please visit glass.org for more information on glass and glazing. We look forward to serving you again soon.